All right, chemistry, this is your video lecture for section 4 of chapter 22. In this section, we'll be talking about nuclear fission and nuclear fusion. Your objectives: define nuclear fission, chain reaction, and nuclear fusion, and distinguish between them. Not only know what they are, but know how they differ. I also want you to explain how a fission reaction is used to generate power. This is a major topic that's going to be discussed over the next several decades as the push for new and alternate energies becomes a constant headline topic. This is going to be one of the possibilities, one of the things that I believe that you and I will need to vote on in the near future. I also want you to discuss the possible benefits and current difficulty of controlling fusion reactions. We cannot control fusion reactions at the moment. Too intensive criteria are required for fusion to take place, and we don't really have the measures in place to make that a controllable action. So let's start with nuclear fission. In nuclear fission, a very heavy nucleus splits into more stable nuclei of an intermediate mass. So we got heavy splits into more than one intermediate. Large amounts of energy are released. Okay, this is why nuclear power is such a temptation for a lot of people, because so much energy is available. So much energy is produced with not that much fuel. Nuclear fission can occur spontaneously or when nuclei are bombarded with particles. And you can guess which one we use in nuclear power plants. We got to start this action by a bombardment with particles. Nuclear chain reactions. A chain reaction is a reaction in which the material that starts the reaction is also one of the products and can start another reaction. The minimum amount of a nuclide that provides the number of neutrons needed to sustain a chain reaction is called the critical mass. So that's the minimum amount of nuclide that provides a number of neutrons. So how many nuclides do you need to get your certain number of neutrons? It's called critical mass. Nuclear reactors use controlled fission chain reactions to produce energy and radioactive nuclides. One of the things that is commonly used as fuel is uranium-235. We will induce a fission reaction by bombarding the uranium-235 with a neutron. Once we do that, we can start a chain reaction, because once this uranium-235 splits, undergoes that fission reaction, not only does it split into two, we have a krypton nuclide and a barium nuclide, we also produce 3 neutrons that are, pretty high in energy. They're moving pretty quickly. So we started with 1 neutron. As a product, we actually had 3 neutrons. So going forward, we actually have everything that we need to start 3 more of this exact same reaction. Each of these neutrons will find another uranium-235 nuclide and create the same reaction, generating 3 more neutrons each. After the second stage, we're up to 9 now, and on and on and on and on. This is what we mean when the particle that starts the reaction is also one of the products. In this case, it is the neutron.
A fission reaction is initiated when a neutron strikes a nucleus of a fissile element such as uranium. Fissile simply means that the element is a good fuel for nuclear fission. If the neutron with the right energy strikes the nucleus, it can split into 2 daughter nuclei. Some additional neutrons are released. These neutrons can trigger another round of reactions. If there is enough fissile material present, this chain reaction can lead to a release of enormous amounts of energy in a fraction of a second.
Nuclear power plants use energy as heat from nuclear reactors to produce electrical energy. So we have these nuclear reactors where the fission reaction that we just looked at is occurring. Another result or another product of those reactions is heat. That heat is transferred into other moving parts that generate electrical energy. There are 5 main components of a nuclear reactor: shielding, fuel, control rods, moderator, and coolant. First thing we're going to look at is shielding. Shielding is radiation-absorbing material that is used to decrease exposure to radiation, especially gamma rays from nuclear reactors. You might ask, why especially gamma rays? Because they're very high energy. And if they're very high energy, they're potentially very damaging, as we talked about the last time we met in class. This also refers to the shielding and penetrating ability of different types of emissions. Remember, one type of emission can penetrate paper, or should I say is stopped by paper. One type of emission is stopped by concrete and lead. We need radiation absorbing material. Typically, these are going to be the very thick concrete walls, maybe lined with lead, things like that. Moving on to fuel. Uranium-235 is typically used as the fuel for fission reactions. Uranium-235. One of the reasons is we don't need too many things to start this reaction. Obviously, we need a mass of uranium-235, but the only thing we need in addition to that fuel is to hit it with a neutron. Right? That same reaction will propagate and create that chain reaction, starting the whole thing on itself. We don't have to do anything to keep that reaction going. Number 3, the coolant absorbs the energy as heat that is produced. So the coolant is what takes in that heat and stores that heat, which will later go into probably driving a steam turbine to generate the electrical energy. But then we have control rods. Control rods are neutron absorbing rods that help control the reaction by limiting the number of free neutrons. Remember the fission reaction with uranium-235 that we just looked at? Each time there is a reaction, 3 neutrons are generated, right? You supply 1 neutron, 3 are generated. Well, the next step, there's going to be 9, and there's going to continue to be exponential growth in that way. Well, if there's exponential growth, that means the rate at which this reaction is going to continue is going to increase exponentially. If that happens, you're going to generate too much heat to be controlled, and you're going to start a meltdown. So control rods are put into place to absorb some of these extra neutrons, reducing the number of particles that can start or continue a chain reaction, therefore limiting the speed and rate at which these reactions occur. A moderator is used to slow down the fast neutrons produced by fission. Again, we're trying to control the rate at which these reactions happen. So we're actually slowing down the speed at which these neutrons operate.
Nuclear fission occurs when a large nucleus splits into 2 smaller nuclei. Normally, fission is initiated when a neutron collides with a heavy nucleus, such as uranium-235. The collision splits the uranium into 2 smaller nuclei. On average, 2 to 3 neutrons are also produced. Fission is an extremely efficient source of energy. 1 fuel pellet of uranium releases as much useful energy as 1 ton of coal. The waste created by the process is also small in size. It is, however, radioactive and will remain so for thousands of years. Methods for transferring and storing these wastes are key challenges in the use of fission as an energy source. Currently, 20% of the electricity used in the United States is produced by fission. It also powers the largest ships and submarines in the U.S. Navy.
Now, this is a diagram of a generic nuclear power plant. Okay, it's simply a model. This is actually something that you're going to need to know for your quick write for this pair of sections. You're actually going to be required to draw a diagram pretty similar to this. So what we see here is we have the nuclear reactor. So this is where both the fuel rods and the control rods are going to be placed. Around these fuel rods and control rods, we're going to find both the moderator and the coolant. So we're going to have something that is going to slow down some of those speedy neutrons and also absorb the heat that's being generated from these nuclear reactions. So you have the control rods, the fuel rods, and the moderator and coolant in the nuclear reactor. This water, okay, this high-pressure water, this coolant is going to absorb the heat. It's going to expand because when things are heated, they expand, they become less dense. And so they're going to rise up. They're going to move through this pipe right here into this area where we simply have water, regular old water, that's going to be exposed to this high temperature liquid, depositing that heat into the water, causing that water to evaporate. Okay, we're creating steam here. And that steam will obviously move up because that's where steam goes, and it'll move through this steam turbine. Okay, this is going to create the electrical current. Once that steam has created the electrical current, it will slow down, it will condense, right? It'll move from the gaseous form back to the liquid form, and then it'll drop into this water tank again. It'll be pumped back into this heating chamber, and the whole cycle will continue on and on and on. But let's look at nuclear fusion. Nuclear fusion, you can think about it as the opposite direction of fission. In nuclear fusion, low-mass nuclei combine to form a heavier, more stable nucleus. So we're going from low mass to high mass, or at least higher. Nuclear fusion releases even more energy per gram of fuel than nuclear fission. So we get more energy in fusion than fission. If fusion reactions can be controlled, they could be used for energy for future generations. Now, this is a big if. If fusion reactions can be controlled, they can be very, very useful. But at this time, not a lot of control going on with fusion reactions.
When light nuclei collide, they can undergo fusion reactions and release energy. Fusion reactions make heavier nuclei from lighter nuclei. When 4 hydrogen nuclei combine, they can form a helium nucleus. Since 2 of the protons have turned into neutrons, other particles must be produced that will balance the charge. These particles are called positrons. Fusion is the principal reaction that causes the sun to give off light and heat. It releases even more energy per gram of fuel than nuclear fission, and its waste products, primarily helium gas, are relatively harmless. Fusion, however, is not used to produce electricity today. Temperatures over 100,000 degrees Celsius are required for fusion to occur.
All right, chemistry, that's going to do it for this section's video lecture. I will see you next period.